Our first goal is to build the Lagrangian for a spin 1/2 field. So we will start with what we did for the Klein-Gordon Lagrangian, which is a free scalar field. The quadratic term is just the first term of a polynomial expansion, and we only keep the quadratic part in order to get a free field. The first term involved covariant derivatives. In fact, we started with only one covariant derivative, because we wanted the Lagrangian to carry a dynamic part that is a time derivative of the field. But the time derivative has to be part of a covariant derivative because we want a symmetric treatment of space and time. And in doing so, we bring a Lorentz index which we need to contract with another Lorentz 4-vector in order for the Lagrangian and the action to be a scalar. And in the Klein-Gordon case, we did that with another covariant derivative of the field. But we argued that we could have something else, for instance, a constant, which will be a constant 4-vector. So we will introduce a new field psi, which will obey a Lagrangian, in which there will be only one covariant derivative contracted by a Lorentz 4-vector. By convention, we will introduce a I factor, and we will multiply again by the field, because at the end we want the Lagrangian to be quadratic in the field. That way we will be able to write a Gaussian path integral and therefore solve the path integral for free field theory. However, there is no guarantee that psi is Hermitian or real. So it's possible that what I need to multiply not by psi, but perhaps psi star, the complex conjugate, or psi dagger, the Hermitian conjugate, or it could even be something more complicated. So I will multiply by psi bar, and I will determine later what the bar means. The requirement is that at the end the action has to be a scalar and a real number. Finally, I should also have a mass term quadratic in the field. However, if I look at the dimension, I see that now this term should be proportional to m and not to m squared. And that's because I have only one derivative. In the Klein-Gordon Lagrangian, I have two derivatives, which each of these derivatives is equivalent in natural units to an energy. And therefore I need to bring an m squared for the mass term. Now I have only one derivative, and if I assume that gamma is dimensionless, therefore I should have only one mass m. Note also that there could be a prefactor in front of m. However, I can always reabsorb it in the definition of the field and also in the constant gamma. So this is the expression for the Dirac Lagrangian. It was introduced so that the Lagrangian is only linear in the covariant derivative of the field. And it came as a surprise to Dirac that eventually this Lagrangian described spin 1/2 fields. But before we can see that, we need to determine what are the constant gamma. For that, we will require that in the classical limit, the field must obey the Klein-Gordon equation. And the argument is the same as what we used for vector fields. We want our particles, which are disturbance of the field which propagates on mass shell, to obey E squared equal P squared plus M squared. And we know from relativistic quantum mechanics that solution to the Klein-Gordon equation will indeed describe particles which are on mass shell. But we also know that in the classical limit the equations of motion are given by the Euler-Lagrange equations. Where we take the case without source. Note that we have two equations, and that's because now we have two variables which we have to treat as independent, psi and psi bar. So let's take the second equation because it's the simplest one. You see that there is no derivative of psi bar in the Lagrangian, in the Dirac Lagrangian. Therefore, this term is simply 0. We see that we don't get the Klein-Gordon equation, but instead we get the famous Dirac equation. Nevertheless, we can require that psi should obey both equations, and as a result that will fix the constant gamma. The Dirac equation is linear in the derivative and in the mass. Therefore, if we want to get a quadratic equation in the derivative and in the mass, we need to multiply by something which is function of the derivative and the mass. So we will multiply the Dirac equation by I gamma nu del nu plus m. Gamma is a constant, therefore it commutes with the derivative. I can always write something as half of itself plus half of itself. In the second term, I have swapped nu and mu because they are just dummy variables. The covariant derivative commute with itself. I have introduced the anticommutator, which I can then use to rewrite the initial equation. We see that all we need to do to get the Klein-Gordon equation is to impose this term to be equal to the metric, so that we can raise one of the Lorentz index of covariant derivative and then obtain a del squared. So the fundamental equation which the constant gamma must obey is that its anticommutator should be equal to twice the metric.